Hello, it's James from XRobots.co.uk. This is part 4 of my 3D printed R2-D2. In fact, it's going to be an R6 droid. So let's see what we've got. Last time I did the frame in the last few videos, and I got as far as building the shoulder hubs, which we need to motorise, and I need to put the other one on. And I also got as far as making part of the mechanism for the sliding centre foot. So let's take a closer look. All of the parts for this frame so far have been printed on a Lulzbot TAS 4, so I've got a lot of 5mm sections. The majority of it's two 5mm sections stuck back to back to make a 10mm section, including this part, and this has also got Ninja Flex rubber rollers, so it rolls up and down the rails. So the shoulder mechanism we can see there has got a pulley on, and that's going to be driven by a motor which is underneath that, which is behind the side vents on each side. The centre foot mechanism, however, we need to sort out first so we can see how much space we've got. So I've got the rails there so it slides and it locks into the square hole so it's nice and stable when it's at the bottom. And the plan to drive that up and down is going to be a piece of threaded studding which is going to be spun by a motor, and there'll be a nut, of course, attached to the carriage so it rises up and down as the studding turns. So I cleverly left a nice recess in each side here, so when this is at the top there's still a way of attaching the mechanics to the frame. So what we're going to do is take the top two rings and attach an H section that passes through this middle piece and is fixed to the sides, so that this can rise all the way to the top, and there's still somewhere to hold the motor and probably a belt drive to turn the studding. So this is the piece of studding that I'm going to be using, and this studding has got roughly 6 threads every 10mm. So to move the nut, which I've got here, which is one of these hex-shaped nuts, that needs to move up and down this shaft in roughly about 5 or 6 seconds. We really don't want it to go much slower than that. And basically working out the calculations, that means that this shaft has to move at roughly 1800 revolutions per minute, which is fairly quick. So I could just couple that directly to an appropriate geared motor, but there's actually going to be quite a lot of torque required to spin this. So the motors I've looked at are these, which are the Como Drills 919D series. So these are similar to the motors I used for Hulkbuster's elbows, and these only have a 6mm shaft on. So I could couple that directly to the studding, but there'll be quite a lot of force on that shaft, even if the motor is geared appropriately. So in fact what I'm going to do is put a smaller pulley on the shaft and then use a further reduction so that the majority of the torque is actually on here. So we're going to use a much bigger pulley, so this is geared 3:1, and that can be really firmly attached to the shaft using this 3D printed thing that I've already made. And then we're not putting so much force on the motor, we're putting 3 times less force on that motor shaft. So the 3D printed thing here is quite a simple thing. It was going to be screwed onto this metal pulley. In fact, I couldn't find any appropriate screws, so I've just shoved some bits of steel in, but it's a very tight fit indeed. It won't pull off and it won't rotate independently of the piece of plastic. And this plastic piece is printed solid, and I've used a hose clip there to clamp the shaft in, so that's actually fixed on extremely firmly. And that's going to be spun in a pair of bearings, and then obviously the nut will be attached to the carriage. So we need to print the other parts off and see how that's going to fit into that H assembly at the top of the frame. So here's the CAD drawing of the frame, and you'll notice the addition of these green and yellow parts either side of the red part. So the red part, of course, is the carriage which goes up and down. Let's just get rid of that. So what we've got are these pieces that bridge the frame either side. Now you can see some stuff lying on the ground there. So the two green parts are basically a top and bottom of a box that bridges those green and yellow parts, and there's some slots in them. You can see the blue part lying on the ground there, which is already the piece I've shown you. And there's 2 other parts. The yellow part here is the motor mount, and the other blue part is a piece with a window in, which is to mount the motor on, and that window there is for the pulley, for the drive belt to go through between the 2 pulleys. And you'll see there's some recesses in the top and bottom parts, and those for bearings to be mounted in. So we'll get all those printed off, and then hopefully we can assemble it and it'll be a bit clearer how it's going to work. I've got all those parts printed out. I've already assembled these panels that were made in green and in yellow, so those are 2 pieces bonded together with the seam line offset, of course. So I've got the two sides, I've got those top and bottom pieces that have got the bearings in. They're fixed in really well and they're both going to face down, so they take the load of the foot pushing the bearing up. The bottom one I've put this extra piece on to hold the bearing in, so when it's retracting the centre foot it doesn't pull the bearing out. Then I've got various other bits including the motor and the motor mount. So the brackets on these motors, this is the Como Drills 919D 2 to 5.1 ratio. The brackets are a bit bendy, so I've made this additional plastic piece that goes on so I can fix that down nice and securely. And I've got the belt there which should go through to the pulley on here. And I've also got some additional pieces. I've got another stopper I can clamp with a hose clip so that I can hold that in place underneath the bottom bearing. So let's have a look in the Droid and get that assembled. So I now have both shoulder hubs fitted. So those are both mounted on their bearings, and what I've done is extended these bits of studding, so these bits sticking in are the ones that travel all the way through the leg, and they're the ones that are going to hold the foot parallel, so they come right through to the outside. So as well as being braced across here and braced onto the centre mechanism, I'm also going to use them to conduct electricity to send data down to the feet to tell the feet motors to drive. So each foot is going to have its own battery and its own motor controller, and I'll send the data through here, so that's how that's going to connect to the legs. So we've got these panels printed, let's just see where they fit. They've got shorter and longer bits to fit onto the rings, so I need to put those in the right way round. So that one goes in there, and these long bits of studding actually pass through there, there's holes in them. So I've left these holes in, which this studding is actually going to bolt into, so I've left the nuts on that you can just about see in there, which will get tightened up and that will be compressed for extra support. So obviously once these are welded in, we're never going to be able to get the centre foot mechanism out. So I need to make sure I do this correctly, and I actually need to put some washers on here before I acetone weld these in. They're pretty, I can just about get them in and they're fine. So obviously we need to space these correctly and get this welded in as well so they're nice and straight, and we also need to put these bearing holders in. So the top one is actually screwed in, as well as the plate to hold the motor so that we can get them out and change the belt eventually. The bottom one is acetone welded in, so I need to make sure I put that in the right way round to match the top one to match the screw holes, which goes there. So that just will pop in, and I'll acetone weld all of that together. And then we can add the motor mount, which fits on that side, and the top one here, which should just slot in, and those two pieces screw in. Obviously not forgetting to put in this piece, and then we can start motorising it. Put the nut holder on the bottom, and we should be able to motorise the centre foot. So these are all clamped up and the parts are setting up. Now they're acetone welded in. I've done my nuts up on those bars, so this thing is now constrained in the middle. And what I've got is the thing inserted there. So I've got a little spacer at the bottom so it rides on the washer nicely, on the bearing nicely, and we've got the belt installed, and then the top part will screw in and we can put the motor onto this piece so the pulley faces through the window, and that will fit in here. So we can also put some packing in to bring the motor out at exactly the right distance to this, which is probably going to need a small plate printing or some sheet material so that we can tension the belt, but there's plenty of space to bring that out, and it's made so it's almost exactly right. So I can get that installed. These two pieces will screw in. This is welded in at the bottom, but essentially it means I can always take this top plate off to get to the belt mechanism. With that all together, I'm really happy that my centre foot mechanism comes right up here and everything fits really well together. So obviously you can see the motor in there. All of this assembly fits within the centre and everything aligns, allowing the centre foot to come right to the top. So looking underneath this, what we need now to do is have something which attaches this rod onto the carriage with one of the nuts so that it can ride up and down. So had I planned this better, I would have made a special keyway in this piece for something to fit across here. I didn't, and I didn't actually know where this rod was going to end up until I designed the top part. So basically I built that the wrong way round. But what in fact I'm going to do is insert this piece, which holds the nut and that is going to be done up tight with another one of these hose clips to grip this piece. So that's going to go that way up, and it's also got these little wings on it which fit neatly underneath the curved part. So I should be able to put that in, and that will hold the nut onto the centre foot mechanism. So then it should rise up and down as the nut turns. That is acetone welded in and is holding this securely. And I should point out that when the centre foot pushes up, it's pushing against the little wings and the nut is getting pushed into the block. So it's only the other way around, of course, when it lifts the centre foot, which is relatively little weight. So I've got a couple of batteries up here. I've just got 7.2 volt NiCad racing packs, or nickel metal hydride packs. So I'm running this on 14 volts. It'll probably eventually run on 12. I'm just going to give that a spin up and down a bit. It runs pretty well. So that's going up, and we should be able to take that all the way down so that it homes into the hole in the bottom. And there we go, and then that's nice and stable, and that clunk was one of the batteries falling down, by the way. I have some adjustments to do to the belt mechanism, but apart from that, it's running pretty well. So my belt isn't very tight, so it runs nice and fast. That does occasionally mean that the teeth ride over the teeth on the big pulley. So I'm going to try and find a more flexible belt. It's just a T5 belt, so fairly easy to come by, perhaps even a thinner one, or I might try printing one in NinjaFlex. I'll just show you that spinning from this end. On the whole, it seems to run okay. So let's have a look at these shoulder motors. So the motors I wanted to use to spin those big pulleys that I've got on my shoulders are these, which are the Como Drills 810-1. These are fairly chunky motors with spur gears, and I've got my batteries again here so we can power one of these up. Hopefully you can see how fast that's turning. So there's a flat on the gear there. So it's going quite slowly. It's doing about 1 revolution every 5 or 6 seconds, something like that. So these will be great. The only issue is they're very, very long and they don't fit in now I've got the centre foot mechanism in. The rating for these is about 6 kg per centimetre of torque, which means that 1 centimetre radius, the stall torque is lifting a 6 kg weight. So basically it would lift a 5.99 kg weight on a 1 centimetre radius, which is a fair amount of torque. So what I really needed to do was track down some motors which, instead of using spur gears that go straight along and an output shaft on the other end, basically it's a right angle. So I found some motors on eBay which claim to have 8 kg of torque. And these are driven by a worm gear and some other gears, so we get this right angle, so I can fit these in sideways, each side of the Droid, and there's plenty of space for them. So obviously the motor on here is considerably smaller, which worried me quite a bit. The speed that they turn is roughly the same, possibly slightly slower. So if we just power this one up, a lot quieter though, which is nice. So you can just see the bit easier to see that gear turning. So it's doing 1 revolution again around every 6 or so seconds. And these are, as I say, claim to have 8 kg of torque at 1 centimetre radius. So this is going to be geared 10-1. On those pulleys. Roughly the circumference of this pulley is roughly 10 times smaller than the big pulleys on my shoulders, which gives me 80 kg per centimetre of torque. And obviously it's going to be 2 of them, so it's going to be one on each side, so that's going to give me 160 kg per centimetre of torque. Now unfortunately R2-D2's legs are more than 1 centimetre long. Of course the leg on the life-size Droid is something like 80 centimetres. So it's nearing 1 metre, and as obviously the radius gets longer, the torque gets exponentially less. So if that lever got longer and longer and longer, obviously the force you could actuate on the end would be much less than it is close up. So that got me thinking actually about why do we actually have these motors in the shoulders? Why do we use those to drive it in, into 2-leg mode and back into 3-leg mode? Because it needs quite a lot of force. So it basically struck me that if we consider the pivot there, it would be far better to use the wheels driving along the ground to push the legs together. So that would of course involve putting a brake on the centre foot there so that it doesn't just roll along, but then we could just drive this wheel, which is going to have a motor in it anyway, along the ground, and that could push it into 2-leg mode and back to 3-leg mode. So the best thing we need is a brake in the shoulder, so we can sort of lock it in position in either position. These motors cannot be back driven, so they may end up sort of being assisted by driving along the ground with the feet. And it does mean having a brake in the centre foot, which is tricky to do with traditional casters. It may mean putting some sort of omnidirectional wheel in there, but that's definitely a consideration. So even though these motors seem wildly undersized, I'm actually going to fit them anyway, and we'll see how it goes when the legs are on. So first of all, I've changed that belt on the centre foot mechanism for a much thinner one. So the previous one is this one, which is actually quite rigid. And I've changed it for a much more floppy one, which is only 6mm thick. It's still got reinforcement in, but it's much more flexible. So now this runs really, really fast. And basically I'm really happy with that. I haven't bothered trying to print one in NinjaFlex, but that works really well. And that's a standard size belt that I just bought off the shelf. It's 305mm in circumference. So here's my first right angle motor assembly, which is attached to this bracket, attached to the upright. It also has a piece attached to the centre panel, so it's nice and braced in there. And what I've actually done is coupled the belt onto this shoulder. So obviously it only does 36 degrees, it doesn't need to turn round and round and round. So in fact the belt is coupled top and bottom with a thing that bites on the teeth, and a screw goes right through the belt. So the belt can't slip because of the gripper for the teeth on the bottom of the belt, so that holds in place very well. There's actually no way to tension the belt now. I was considering having a presser basically top and bottom to pinch that belt round the roller a bit, but for now it works quite well. There's some slack in it, but it's not too bad. So let's just give that a spin and we can see the sort of speed that that drives at. So that is at one end, and let me just drive that the other way. So we can see it goes pretty slowly. I've got no end switches at the moment, so I have to be cautious, but that's at the ends. And then we can see that's actually fairly firmly locked there. So that works quite well. Let me just drive that back the other way. And that's the other ends, and that again is fairly well locked in position. So I'm pretty happy with that. It's got quite a lot of torque on it. I think it's going to be okay to pull the wheels along the ground, but we won't know really till we get the legs on. So if I try and stop that, I kind of can, but yeah, the belt will skip eventually. But I think that's pretty much okay. The motor is definitely powerful enough, even if the belt is too stretchy. So other way of doing this, of course, is to have a piece of cord which is coupled, goes round the belt at once, is then coupled to the pulley, and then goes around another time and then is coupled again back to the big pulley. So we could just use a piece of nylon paracord or something like that instead of a toothed belt and actually couple it to this, allowing it only to turn 360 degrees and this turning 36 degrees, so we still get the same gearing ratio, but basically there's no chance of the belt slipping. But actually I think there's enough torque to just drive those feet along the ground, and if we use assistance from the feet driving as well, then I think it's going to be okay. I get a kind of bad feeling about it though. It's not my favourite piece of engineering, but I'm going to leave it there until we've got the legs on and we can tell what's going on. The worst case is that I just abandon this bracket and I've still got plenty of space down below to put a much bigger motor if I need to, or in fact just a linear actuator like everyone else. But at the moment I'm sort of about 80% hopeful this is going to be okay. So I've got both motors fitted now and both belts, and I've actually tensioned that belt up, so the other one that I managed to get on a bit tighter, and I've pulled the other one up as well. So I've actually moved it up a notch by basically moving it one tooth on the equivalent part that's underneath, actually attached to the roller. So that's actually locked into the tooth, and I've pulled them up quite tight, so you can almost play them like a guitar string. And now that's much firmer. So if we take this one to its end stop, wherever the wire is, let me just find the other one. So that's about the end, and then that really is, you can move it a bit, but it's actually the play in the studding between the inner and the outer, so the middle there is really locked, and I don't think I can make that skip on the belt by moving it by hand at least, so that's going to be good enough for driving and standing up in 2-leg mode. So that's all I've got for this part of the build, but don't forget to subscribe to my channel and check out for future updates to see how those motors work out once we start building the legs up, which is the next thing that I'm going to do.